So for number 7, we want to prove all these statements. And to prove them, we're gonna use these definitions here, which I've written down. So the first one is the definition for an odd number. So x is odd if and only if there exists an integer m such that x is equal to 2m plus 1. Y is even if and only if there exists an integer n such that y is equal to 2n. And lastly, a divides b if and only if there exists a c belonging to the integers such that b is equal to ac. So we're going to use here these definitions, and we're assuming that a, b, c, and d are integers. So I'm going to say assume a, b, c, d belong to the set of integers. And I'm just going to leave this, up here so that I don't have to keep saying assume that a is an integer, right? I'm just going to leave it there and I'm not going to repeat it since I'm proving all of these at once. However, if you're doing them separately, you would want to every single time say assume that a is an integer. So that being said, let's get started. So for a, we want to prove that 2a minus 1 is odd. So we want to transform it into this line right here, which is 2 times an integer plus 1. So what I'm going to do is I'm going to go 2a minus 1 is equal to, I'm going to turn that minus into a plus by saying that it's equal to 2a minus 2 plus 1, which is equal to, I'm going to factor out the 2, so that's 2 times a minus 1 plus 1. Okay, so once I've done this, I have turned it into a form with my definition, right? A minus 1 belongs to the set of integers because the integers are closed under subtraction. So 2a minus 1 is odd. So I've proved the first one. Actually shouldn't have been 1, it should have been a, right? So for item B, we have that if a is even, then a plus 1 is odd. So we're going to say assume a is even. So if a is even, then there exists an integer m belonging to the set of integers such that a is equal to 2m. So we have used the definition for even. So a plus 1 is going to be equal to 2m plus 1. And then this clearly satisfies the definition for odd number, right? Because m is an integer. So say m belongs to the set of integers. So a plus 1 is odd. So a plus 1 is odd. Okay. For C, they want us to assume if a is odd, then prove that a plus 2 is odd. So we assume that a is odd. So assume a is odd. Then there exists an integer m belonging to the set of, there exists an m belonging to the integers such that a is equal to 2m plus 1. So when we have that a is equal to 2m plus 1, then we're going to go a plus 2 is equal to 2m plus 1 plus 2, which is the same thing as, I'm going to group the 2's, so that's going to be 2 times m plus 1 plus 1. So m plus 1 belongs to the set of integers, so a plus 2 is odd. So we have shown that it is odd using the definition for an odd number. Okay, let's do D. And D says that a times a plus 1 is even. So for D, we're going to have to go into cases. And actually, I'm going to just erase all of this so that we have room. So we're going to have to go into 2 cases, if a is odd or a is even, right, for D. So I'm going to go for D, case 1, a is odd. So if a is odd, then there exists an m belonging to the set of integers such that a is equal to 2m plus 1. So a times a plus 1 is going to be equal to 2m plus 1 times 2m plus 1 plus 1, so that is 2m plus 2, which is going to be equal to, let's see, 4m squared, and then I'm going to have 4m plus 2m, so plus 6m plus 2, which is equal to, I'm going to factor out a 2 times 2m squared plus 3m plus 1. Okay, and we can say here that 2m squared plus 3m plus 1 does belong to the set of integers, so a times a plus 1 is even. Okay, so we have shown that a times a plus 1 is even when a is odd. Now let's look at case 2, which is when a is even. So we have case 2 when a is even. So then there exists an n belonging to the set of integers such that a is equal to 2n. And so we have that a times a plus 1 is equal to 2n times 2n plus 1. And now I'm just going to leave the 2 outside and distribute the n is equal to 2 times, let's see, that's going to be 2n squared plus n. Okay, and then we say 2n squared plus n belongs to the set of integers, so a times a plus 1 is even. So we have shown here that in both cases, a times a plus 1 is even, no matter the parity of a. Okay, so for E, we want to go that 1 divides a. We want to prove this. So E, we want to prove that 1 divides a. So let's think about how we're going to do this. Well, let's just say that a is equal to 1 times a, right? This is just a tautology. And so if a is equal to 1 times a, if you look here at the third line at the definition, this implies that 1 is a divisor of a, right? So we say by definition, actually, we're going to say a belongs to the set of integers, so by definition, 1 divides a. Okay, so this one was pretty straightforward. We just used the definition of a number that divides, right? So now we are done with E. Let's do item F. So item F is we're going to have the same idea. It wants us to prove that A divides A. So let us write that down. So for item F, we have that A is equal to 1 times A. It's going to be the same logic. We have to say, okay, A is an integer, right? Because we're assuming that A is an integer to begin with. So by definition, actually, not A is an integer, 1 is an integer. 1 is an integer, so by definition, we have that A divides A. Yeah. So we've just been using definitions. Okay, let's go to the next one. The next one is if A and B are positive and A divides B, then A is less than or equal to B. So let's go ahead and do that. So we're going to say assume A and B are positive and A divides B. Well, if A divides B, then we look here at the third line, right? Then by definition, there exists an integer C belonging to the set of integers such that B is equal to AC. So we have just used the definition, right? And so, and we know that if A is greater than 0 and B is greater than 0, C is greater than 0. That's the only way that it could work out, right? If left-hand side is positive and A is positive, it must mean that C is also positive. And so if C is positive, it must mean that A is less than or equal to AC because C is positive. And so A is less than or equal to, because AC is B, A is less than or equal to B. And so we have proof that if A and B are positive and A divides B, then A is less than or equal to B. Okay, let's go to H. Assume A divides B. So if A divides B, then there exists a C belonging to the set of integers such that B is equal to C, AC, right? Such that B is equal to AC. And so if B is equal to AC, we're trying to show that A divides BC. Okay, so then therefore BC is going to be equal to, let's see, BC is going to be, then I chose the, because C is already being used, so I should have chosen a different letter. Let me choose K. So we're going to say B equals AK. Okay, then BC is going to be equal to, AK times C, because B is equal to AK, right? Which is equal to, let's see, A goes outside, and that is KC. And so we have shown here that, and actually we're going to say that KC belongs to the set of integers, so A divides BC. Let me see if that is right. Yeah, that is right. So that is it for item H, and we are almost done. Let me erase all of this. Okay, now we're going to item I. So for item I, we have that if AB are positive and product AB is equal to 1, then A is equal to B is equal to 1. So we begin by assuming this. So assume that that A, B are greater than 0 and AB is equal to 1. So let's see. If AB is equal to 1, then it means then B divides 1, right? It fits the definition here in line 3 of a number that divides. Then B divides 1. But the only factor of 1 is 1, right? But the only factor of 1 is 1. So B is equal to 1. And so if B is equal to 1, we have that A times 1 is equal to 1, right? Therefore, A is equal to 1. And so we have our conclusion that A is equal to B is equal to 1. So we have proved what we wanted to. So that is it for item I. What about item J? We want that if A, B are positive, A divides B and B divides A, then A is equal to B. Okay, so let's prove that one. Okay, so for this one we have assume A and B are positive and A divides B and B divides A. B divides A. Then there exists integers C, D, so CD belonging to the set of integers, such that A is equal to BC and B is equal to AD. Okay, so we have just used the definition. Actually, I should have put this is item J. So we've just used the definition of a number that divides, right? And so if A is equal to BC, it's going to mean that, let's see, that B is equal to A over C. Well, if B is equal to A over C, this implies that when we substitute this in here, it implies that A over C is equal to AD, right? And so if A over C is equal to AD, if we divide both sides by A, we have that 1 over C is equal to D, right? So for that to be true, and we have that 1 is equal to DC. So what happens here? This means that D divides 1. It fulfills the definition for a divisor, right? But the only factor of 1 is 1. So if the only factor of 1 is 1 and D divides 1, therefore D is equal to 1. And so 1 is equal to 1 times C, and C is equal to 1. So what we have here, thus, C is equal to D is equal to 1, and we have proved here, actually we haven't, we still need to move ahead. So if C is equal to D is equal to 1, then we have that A is equal to B times 1, and B is equal to A times 1, so A is equal to B. Okay, now we have proved it, right? So that is it for item J. Now let's do item K. So item K says that if A divides B and C divides D, then AC divides BD. So let's go ahead and write this in. So for item K, assume that A divides B and C divides D. So assume A divides B. Actually, I wrote this terribly. A, B, and C divides D. Well, then there exists integers M, N, such that if A divides B, it means that B is equal to AN, and D is equal to MC. Let me see if that's right. C divides D. Yeah, that is right. So let's see. Therefore, we have that BD is going to be equal to AN times MC. Let me just improve my handwriting a little bit. Yeah. Which is equal to AC. I'm going to pull that outside. NM. And so we have that NM belongs to the set of integers. So AC divides BD. So we're just using the definition of a number that divides, right? So that was K. Let's do L. If AB divides C, so assume AB divides C. Then there exists D belonging to the set of integers such that C is equal to A, B, D. Okay, so if C is equal to A, B, D is equal to A outside and B, D inside. And I'm going to say, okay, B, D belongs to the set of integers, right? So A divides divides C. So we have shown that. And lastly, we have that if AC divides BC, so for M, assume that AC divides BC. Then there exists an integer D, so exists a D belonging to the set of integers such that BC is equal to D times AC. So if we divide both sides by C, we have that B is equal to AD, and so D belongs to the set of integers, so A divides B. A divides B. And that is it for problem number 7.